Hello. Today we'll be doing some pulleys, but we're throwing a little wrench and they're going to have a mass. Now, this video was by special request and we're going to fulfill our duties quite effectively. As you can see, I already wrote down we're going to have a little direction legend, I guess. Um, it's kind of important to remember because we're going to be obviously when we have vector quantities, signs do matter quite significantly. So we're talking clockwise will be negative and counterclockwise will be positive. And that is that. So back to the whole pulley with mass. Why do I have to include with mass? Well, it's very interesting because I'm just going to quickly sketch a regular pulley. And let's say we just have two blocks. Ignore that little kind of bad sketch. Typically, if this pulley is not massless, we can say that these blocks are connected by obviously they're connected by the same string, but we can also see that that string has uniform tension. The tension acting on this block is equal to the tension acting on this block. Now, let's say we add mass to this. The whole thing with a massful pulley is that now torque can be applied to it. And since torque can be applied to it, we know that if you have an equal torque and if you have an equal torque, there's going to be zero angular acceleration. So if we had the same case where the tension was equal on both sides, the pulley wouldn't move. And if the pulley doesn't move, the blocks don't move. And therefore, it doesn't really make sense. So essentially, we come to the conclusion that the tension on one side is different from the tension on the other. Now, since we have two tensions, it does make things a little more complicated, but we can still solve it nonetheless. So we're going to actually do two problems today. I got two good things in mind. One's going to be a basic pulley problem to get us introduced to the subject. Another will be probably going over some points from 2019 AP Physics 1 FRQ. I really liked it. I think it challenged your critical thinking, whatnot. But, we will start with just a basic mass pulley problem. I believe this is some variant of an Atwood's machine. It's going to be a really basic problem. We're going to give this, we're going to keep it symbolic. That's just how I like to do things. And we're going to have a block of mass m and a block of mass 2m. And now for the pulley itself, again, we're going to keep it a little symbolic. So we're going to say that, okay, I just realized that this point should definitely be in the middle. That's okay. Just, change that a little bit. Okay, great. Now it's going to have a radius r and a moment of inertia I. Now the moment of inertia I, we know the formula for that, so it's we have that in the back of our mind, but we're just going to use I for this case because that's easier. And also we have the radius r. So we have everything we need. Now we're going to create a free body diagrams, which is probably the only reason I stay around for physics. So this one's going to be m, and what we're going to have is pretty clearly our gravitational force acting downwards, and we're also going to have our force due to tension acting upwards, and we're going to denote that as T1. On the other side, we're going to denote it as T2, because again, the whole thing we started with, tensions are different on either side of the pulley. So we have mg and T1, and this isn't part of the free body diagram per se, and if you're on the AP test, you're actually not going to want to do this, but we know that this block is greater than this block in terms of mass, so this one's going to go down and this one's going to go up. So we can say that the net acceleration is this one. And that's just, a little indicator to help us. Again, if you're taking an AP exam, you're probably not going to want to do this, but it can be useful otherwise. Now we're going to do this, and now the mass is 2m, so the gravitational force is going to be 2mg. And differently, it's going to be T2 to denote the second tension. Now, what you'll see is we have, okay, also I'll denote the way of acceleration. But again, now we have our basic setup for our basic pulley problem, but there's mass. So let's add our third and final component into this system. Essentially, we have to use our blocks, but we also, I cannot draw a circle for the life of me, have to use our pulley. So we know that we have tension 1. We're going to have tension 1 this way. I'm just going to illustrate this like this. T1, T2, and this kind of isn't a free body diagram, I guess. Maybe I could do that a little bit better, but what we know is that this tension is going to be greater than tension 1, and the pulley is going to rotate this way. It's going to rotate clockwise, and if we refer back to our chart, that would be a negative direction. But essentially, T2 minus T1, because T2 obviously wins, and this is going to be equal to, this is going to be equal to actually it's not going to be, hold on. We know that, okay. We know that T1, T2 minus T1 is kind of the direction of this acceleration, this net torque. Now we have our net force, and we can recall that the equation for torque is tau equals Fr, and then I think it's cosine theta. We don't really care about the cosine theta in this part. All we care about is multiplying it by R. Because now what we'll see is that this is our F, and then that is obviously our R, and this is essentially tau, or our net torque. Now we know that net torque is equal to I alpha, where alpha is the angular acceleration. And one thing I didn't explicitly state, but I am going to, kind of, I guess, imply, is that this string is not going to stretch, it's not going to slip, it's not going to do anything. It's going to kind of abide by like normal rules. Because of that, we can use something that, we can use the formula, or the equation, I like to call it acceleration equals ralpha, which is an easy way to remember it, but acceleration equals r times alpha. With that, we can solve for alpha and say that alpha is equal to a over r. Now we're going to substitute that into our equation. We're going to say T2 minus T1 all times r is equal to I a over r. Now we want to isolate our tensions a little better. We're going to say T2 minus T1, we're going to divide by r in this case, is equal to IA over r squared. So now we have just our forces here, and we have a valid equation. We didn't actually create the equations for the blocks, but we can do that quite easily. T1 wins in this case, so T1 minus mg is equal to ma, and we know that we know that 2mg minus T2 is equal to 2ma. And then also I will transplant this equation right here, say T2 minus T1 is equal to IA over r squared. Boom. Now we simply add everything up, and that's very similar to your free body diagrams you've done in the past. So we can clearly see that these T2s cancel out, these T1s cancel out, and we're left with 2mg minus mg. And that would just be obviously mg. So we're going to say mg is equal to ma plus 2ma plus ia over r squared. And from that, we are going to, we're going to solve for the acceleration in this case. Kind of forgot about my motive for a second. Don't worry about it. So we're going to factor out a, and then this will obviously become 3ma, so 3m plus I over r squared. Now that's valid, and then we can say that the acceleration is equal to mg over 3m plus I over r squared. I is our moment of inertia, r is our radius, and m is our mass. And that's it. That is our equation. Now, if we wanted to solve for a tension per se, that would be pretty simple. We could rewrite T1 as m times, just m times a plus g, and then we'll plug in a, and then we're in terms of the constants that we abide by. Same thing for T2, a little bit, a little bit different, but I'll just write it down. Twist my arm. Equals 2m, and then it would be g minus a. Again, a little bit different, but same idea. And I feel like that's kind of the extent of what you would want to solve for. I mean, technically you could solve for anything if you want, but those are the two main things. You'd probably be asked tension or acceleration. But that's that. And I want to keep this relatively brief, so let's move on to the second problem. Now, the second problem also incorporates a pulley with mass, but it does it a little bit differently. What we got is a table, and it doesn't look too table-like to me. Just gonna do that for a table. This is our table. We gotta have our block here, and I'm trying to think. Oh yeah, so we actually don't know the masses. It's all symbolic, and we're going to have our pulley. Please stand by with my drawings. Trying to look. I don't. I'm just gonna assume for now, unless otherwise specified, that it's gonna be of r, radius r, and moment inertia I. Now this block is connected to this pulley. Pretend it's a nice drawing, just for me. And then we have block B down here. So you can see a little bit different. And before we get into the questions, again, this is our 2019 AP Physics 1 FRQ, and it's number 2, actually. So in case you want to see the actual thing. This is the foundation, and we're just going to go through free body diagrams, and we're going to construct an equation. Now, on the exam itself, you might want to approach it a little differently to answer the questions appropriately, but, we'll go with the free body diagrams here. So we have MA, and we know that there's going to be a gravitational force downwards. Also, forgot to mention, mu is equal to 0. So we have MAG, gravitational force. We have the subsequent contact force. And then we have our tension 1. Now, on the other hand, we're going to have MB, and we're going to have our similar gravitational force, but we're not going to have our contact force. We're just going to have our tension 2. And that is both of our blocks done. So let's go to our pulley. So we're going to have T2 down here, T1 going to the right. And we don't actually know which is larger, which is slightly problematic. But that's fine. We'll just say that T2 is larger. So let's assemble our equations. For this one, it's just T1 is equal to M sub A. For this one, it's T2. That's not right. We're going to pretend that block B is of greater mass, just for this case. MBG minus T2 is equal to MBA. And finally, T2 minus T1 times R is equal to I alpha. We'll expand this a little bit, do what we did in the other one. I'm going to cut some corners, just say that. Okay, so I did kind of put some liberties because I kind of forgot that we don't know the direction of motion. So I'm just assuming that, the system's going to go this way. That means block A is going to go this way. Simple. Now we're going to add everything up like we did before. It's not in the same vertical structure, but I hope you can fill in the dots. The T2s will cancel out, the T1s will cancel out. Sorry. And we'll be left with MBG is equal to MAA plus MBA plus IA over R squared. Okay. And from that, I assume might be best to just do acceleration. Why not? I'm just going to skip some steps and say that MBG over, and it would just be MA plus MB plus IA, oh, not IA, I over R squared. Now that's that. Oh man, you know what? I just realized something. In this problem, technically, The pulley doesn't have mass. I swear it did when I remembered it. I didn't read the problem before I made this video. Okay, so, I mean, that's kind of embarrassing, but we'll try to roll with it, I guess. I don't think it's going to affect the answers much, but this is our equation for acceleration. And now I'm going to post some questions. I'm not going to write them down because I'm a little lazy. But the idea is they ask, suppose the block of mass A, which would be this one, obviously, is much greater than the block of mass B. And that's essentially saying this mass is it's so large that B can be considered negligible. And we want to estimate the magnitude of the acceleration after release. So, how would we do that? They wanna they want you to first, say the magnitude of the acceleration and then also explain it, and they want you to do that with add equations. They can't really stop you from like, looking at an equation that you derived. So you can do that, but you need to explain it using physical concepts. So if we look at the equation though, if ma is much greater than mb, we can essentially say mb is zero. If mb is zero, the acceleration is zero, just like right off the bat, because the numerator would be zero. So the answer they're looking for, an answer that's correct, is that the acceleration would be very nearly zero, can be approximately zero. It would be so minute it can be considered negligible, something like that. And the reason behind that is that the moment of inertia of this block A is so large in comparison to block B that the force due to block B, due to the tension caused by block B, doesn't really affect the block, and the moment inertia is, too large. And that's that. So now we're going to switch it up and say MB is much larger than MA. Now let's look at that. So we can see that we have MA here, we're going to say that's zero. We're going to have MBG over MB plus IR squared. So in the problem itself, you technically don't have the IR squared. And then there you can see it's essentially free fall. But we do have IR squared here because I mistook the problem. But we can still get the same answer, essentially. Instead of it being, just G, nearly G, it's going to be slightly less than G. Not going to be slightly larger, it's going to be slightly less. Because we're increasing, yeah, I'm trying to think. I guess if R is really, really small, then it wouldn't. So we're just going to assume R is greater than 1. Yeah, we're going to assume R is greater than 1. No, we're not talking R, we're talking, would it be, the square root of R? No, what am I saying? It's always going to be greater. Never mind. Forgive me. I'm just tricking myself. um, so yeah, essentially it's going to, because we're increasing the denominator, the value of our net acceleration is always going to be slightly less than g. So if we have mass in our pulley, it's going to be slightly less than g. If we don't have mass, it's just going to be nearly g. And the reason behind that is that because um, the mass of MA is negligible, this block B is essentially in free fall. It's just falling to the ground. There's nothing stopping it. And that's just that. You're asked then to derive an equation of the acceleration, which we did. We went a little above and beyond with the consideration of mass. Then it asks if your equation agrees with your reasoning. And then also, this is a key concept. It says now the pulley has mass. And this might have been why I got confused. I might remember this. The pulley is replaced by a pulley with mass. Now, when the blocks are accelerating, the tension in the vertical portion is T2. How do the two tensions compare to each other? And that's just saying T2 is the tension with mass and T1 is the tension without. So we know by the principles of a massful pulley that the net torque has to be unbalanced. Thus, in the case where it accelerates this way, it rotates clockwise, T2 is greater than T1. That's not what it's asking. It's asking, is the magnitude with the massful pulley greater than the magnitude without the massful pulley, essentially. And what we have to consider is that because of this net torque, it's because of this net torque, um, okay, trying to word it. Uh, yeah, because of this unbalanced torque, we're gonna have a smaller acceleration for block B because there's kind of like a yeah, we're gonna have a smaller acceleration for block B because of this torque that's unbalanced. Now, because there's a smaller acceleration, we have to go back to our forces and say, how would we get a smaller acceleration? Well, we would get a smaller acceleration if there's a greater tension acting in the opposite direction of the acceleration. So that was maybe a little long-winded, and if you're a little confused, I'd recommend going to the 2019 scoring guidelines. But the answer to that question would be that T2 is greater than T1. Yeah, T2 is greater than T1. And again, the smaller acceleration necessitates that there would be a greater tension acting in the opposite direction. Now, as with a lot of my videos, there's a little mishaps here and there, but we got it at the end. I hope you learned a little something or it was a good review, and that is all. Thanks.